Okay, hi everyone, and hello to everyone online. Thanks for coming. So, for those of you who don't know Alan, we met him at the RCTP conference that we attended a few weeks ago. Was a quantum hackathon, so we just invited him to give a talk on his PhD research. So I'll just give like a quick formal introduction. So Alan is currently a final year PhD student at the at the National University of Córdoba in Argentina. He is under the supervision of Professor Cecilia Cormack. His main interests are cold atom systems and the theory of open quantum systems, particularly out of equilibrium and quantum information. So during his PhD, he studied analytical and numerical trapped ions coupled to optical cavities. So yeah, thank you so much, Alan, for giving this talk, and I'll hand over to you now.
Okay, thank you. Well, the title of this talk is Structural Crossovers in Trapped Ions Dispersively Coupled to Optical Cavities. First, I'm going to comment a little bit about work, which is, so I'm doing my PhD, as I'm studying in the National University of Córdoba under the supervision of Cecilia Cormack, Professor Cecilia Cormack, and also under the co-supervision of Leonardo Herman, who works at the National University of San Martin in Buenos Aires. And some parts of this work have been done in collaboration with Marcos Saraceno, who also works in Buenos Aires in the National University of San Martin. I'm going to comment a little bit of ion traps. So ion traps are experimental setups in which a combination of electrostatic and radio frequency fields are used to confine ions. And the equilibrium positions of the ions within these traps or within these setups is going to be given by the combination of the trap potential and by the electrostatic repulsion between the ions. So, for example, at low temperatures, the ions in these setups can crystallize and form structures in 1, 2, or 3 dimensions, for example, the ones shown here. And a typical number of ions within these setups varies between 1 and 1000, and the typical distances between these ions is between something between 1 and 10 micrometers. In more recent experiments, these setups have been integrated with optical cavities. So, for example, this can be done as is shown in the figure on the left, where the cavity axis is parallel to the ion chain axis. Or this can be done also as is shown in the figure on the right, where the cavity axis is perpendicular to the ion chain axis, and this will give rise to different kind of dynamics. So in this case, now the equilibrium will be given again by the trap potential and the electrostatic repulsion between the ions, but now we have to take into account the optical potential. These systems have several uses. For example, they can be used for cooling of the ion motion. They can be used as a source of indistinguishable photons. And they can also be used for simulations of condensed matter models, for example, models of microscopic friction or structural transitions. I'm going to, during this talk, we are going to be working with the system in the so-called dispersive regime. This is the regime in which the electronic degrees of freedom can be neglected, or we can, and in such a way that we can work with an optomechanical system. So we're going to be thinking that we have just a single mode of a cavity field, and this cavity will be pumped by a laser, and due to imperfect reflectivity of the cavity surfaces, this cavity will have a leakage of photons at a rate kappa. So what's important to note here is now in this situation, the cavity frequency resonance depends on the ion position within the cavity. Here I'm going to comment a little bit about the structural transitions in this system. For example, if we assume that we have the cavity axis or the wave vector, the standing wave potential in the cavity parallel to the ion chain axis, then we can think that we have a linear array of ions, which can be considered in a sliding state if the laser amplitude that is pumping the cavity is below some critical value. But if we raise this laser amplitude, then the ion chain will get pinned in the optical potential wells. So when the optical potential is more relevant to the dynamics, then the ion chain will get pinned in the optical potential wells. This dynamics is similar to that of the Frenkel-Córdoba model, which is a model of microscopic friction. This model consists originally of a chain of oscillators sliding on top of a periodic potential, and so in this way, this experimental setup provides a system in which to test the dynamics of nanofriction. However, there are some difference between this system and the original Frenkel-Córdoba model. For example, that there is a non-uniform distance between the particles in the pin state or in the pin phase. And also that if we use a semiclassical description, which is common in this kind of systems, moreover when we have several ions in these traps, is that if we use this semiclassical description, then we see that there is a regime of bistability where both kind of solutions are valid steady-state solutions. On the other hand, we see that if we assume that the wave vector of the standing wave is perpendicular to the ion chain axis, we can see a different kind of structural transition in which which is the linear to zigzag transition. This transition can be understood without thinking of the optical potential. For example, if we think that we have the gravity trap frequency, for example, if we consider this trap in an harmonic approximation, then if this frequency is above some critical value, then the array within this cavity will be a linear array, will be a linear chain. But if we relax the trap frequency and when this frequency gets below this critical value, then the electrostatic repulsion between the ions will start to be the most important or the most relevant part of the dynamics, and this will push the ions toward this zigzag configuration. Here, if we add or if we integrate the optical cavity within the system, then we can see that this transition can be driven in terms of the amplitude of the laser field that is pumping the cavity. And again, if we use a semiclassical description to treat the dynamics in this system, then again we see that there's a regime in which both kind of solutions are valid steady-state solutions. So we again have a regime of bistability. There are several systems in which the use of a semiclassical description or maybe a mean field description, depending on the system, leads to a dynamical map which has more than one fixed point, meaning that we have more than one steady state in the system. And in all of these systems above, for example, it has been shown that if we consider finite size dynamics, then the Liouvillean gap never closes, which would be what we would expect for bistability, for the bistable regime. But this gap never closes, but just gets smaller and smaller, and meaning that the decay towards the true and single steady state will be slower. So what we want to take is what happens with this bistability when we avoid using this semiclassical approximation within the system. So as a rough comment on what's the dynamics in the system, we are going to consider that we have an atom considered as a two-level system, the ion trap in harmonic approximation. We are going to consider only one single degree of freedom of this ion trap. This single degree of freedom could represent, for example, a single mode of vibration of the ion chains, or could represent, for example, a single ion. In the case of being representing one single mode, it should be the mode most relevant to the dynamics. For example, in the linear to zigzag transition, this should be the zigzag mode. We're going to consider only one mode of the cavity field, and we're going to consider that there's a laser pumping the cavity, and that this laser is detuned respect to the dipole transition of the atom, and it's also detuned with the cavity frequency. Again, we're going to consider that this cavity has losses at the rate kappa, and as I commented before, we're going to consider that we're going to be working the dispersive regime. In this regime, the idea is that the excited state of the atom it doesn't have or the population of the excited state of the atom can be neglected. And this is valid as long as the detuning between the laser pump and the dipole transition sets the shortest time scale of the system. And in this case, the excited state can be adiabatically eliminated, giving rise or giving place to this effective Hamiltonian for the ground state dynamics. So this Hamiltonian only describes the dynamics within the ground state. It includes a Hamiltonian for the mechanical degrees of freedom of the ion. It includes the term corresponding to the laser pump. It includes the energy of the cavity and a coupling between the position of the ion within the cavity, within the standing wave potential, and the number of ions within the cavity. So this is what makes, this coupling is what makes this system an optomechanical system. I'm going to comment a little bit now about the semiclassical approximation that I was saying before. So in this approximation, or the idea in this approximation, is to decompose every operator as a sum of classical equilibrium values and small fluctuations around these equilibrium values. Then we get the Heisenberg equations of function, and we neglect everything that is of second order in these operator fluctuations or fluctuation operators. And here, for example, the results of the steady state solutions of the steady state equation of the steady state, the solutions for the steady state of the classical equilibrium values. That's what I want to say. And just what I want to note here is that in this semiclassical approximation, the classical equilibrium positions for the ion can be derived as the minima of this total effective potential here. So in this case, within this approximation, what we have is that for small laser pump, for small laser pumping, or when the driving of this laser is small, we will have just one solution, classical solution, at around the trap center for the ion. And then, if in the limit of large laser pumping, we will have that there appear two solutions, each located around this the optical potential waves. What happens in the middle, it depends on this parameter that is called the cooperativity. So the transition between these two kinds of solution depend on the cooperativity. So for example, if we have a small cooperativity, the transition will be continuous, as is shown in the figure on the left, where we see the classical equilibrium positions for the ion. And if in the regime of large cooperativity, the transition will be discontinuous, as is shown in the figure on the right. And every time the transition is discontinuous, we will have a regime of bistability. And this is the regime that we are going to be working along this talk. So this semiclassical description has a lot of advantages. It allows to get analytical results. It has a very efficient numerical simulation, and all of the description is in terms of Gaussian states, for which there are lots of results. So, for example, for quantifying entanglement, but it has some problems that it's not always valid. For example, in the few-photon limit, when there are few photons inside the cavity, or near the structural transition between these both kinds of solutions. And also it's not valid if the wavelength of the standing wave potential is smaller than the ion's characteristic spread, but this is not something that we're going to be looking at in this talk. So here I'm going to start with the first part of the talk, where we look at the steady states of the system. And as a first approximation, we work in the few-photon limit, and we do a diagonalization of the Liouvillean. So we are going to look at the steady states, at the eigenstates of at the steady state of the system. We're going to be doing a numerically exact study of the problem without further approximations. Just maybe what we're going to consider is that since we're interested in the transition between the ion being at the trap center and being located at one of the optical potential wells, we are not interested in what happens if we consider the following optical potential wells. We are just interested in the first transition. So what we're going to do is, instead of considering a periodic potential, we're going to consider such a system that the intensity profile of the intercavity field is just given by the two optical potential wells. So in this picture, the effective potential that I was commenting before, the one that which can be used to write the classical equilibrium positions for the ion, looks like this across the transition. Here again we see the ion located at the trap center, the ion located at the optical potential wells, and the transition between these two kinds of solutions as we increase the laser amplitude. So we're going to be looking at the steady in order to look for the steady states of this system. We're going to look for the eigenstates of the Liouvillean, and the steady state will be given by the right eigenvectors of the Liouvillean with eigenvalue 0. In the case of being bistable, or in the case of being bistability, we should find more than one of these steady states, or more than one of these eigenvectors corresponding to a null eigenvalue. We don't expect this to be the case. For finite size systems, what we expect here to see is this slowing down of the dynamics within the transition region. So this would be shown that as a decrease on the spectral gap. So in this case, the appearance of this metastability, this slowing down within the transition region, should be identified as a separation of the real part of the spectrum of the Liouvillean. Here we have, for example, one of the results for this spectrum. We are not looking at the whole spectrum; we're just looking at a portion of the spectrum. Here we have some results, for example, for the steady state mean values. Each of these curves here corresponds to a different value of the cavity loss rate. So as the cavity loss rate gets smaller and smaller, the number of the photons within the cavity should increase, and this transition should approach the semiclassical limit. So here what we see is, again, for example, if we look at the localization of the ion within the trap, we see that for small laser pumping, the ion is located at the trap center. In a regime of large pumping, the ion is located at one of the optical potential wells. And here we have the bistability region marked with these vertical dashed lines, and the change of the global minima of the this effective potential shown with these dots here. Here we see the comparison with the results for the semiclassical approximation, in which the transition should be an abrupt transition or a sharp transition around the change of global minima. But for the exact results, we obtain this smooth transition. We can also look at this transition in phase space. Here in the row above, we are looking at the semi-phase space distributions of the cavity, and in the row below, we're looking at the phase space distribution for the ion. In case the Husimi distributions are just one of many possible quasi-probability distributions to look at the states in phase space. Here, the axis in the case of for cavity represents the field quadratures, and in the case for the ion, the axis represents position and momentum for the ion. And we can see how for small pumping, the ion is located at the trap center with a very small photon number, and in the large pumping regime, we see again the ion located at the optical potential wells with a high photon number within the cavity. And in the transition, we can see how we have two clearly different lobes, each one of these representing one of these states. Each one of these lobes representing one of the semiclassical branches. For example, here the ion at the center with low photon number, ion at the optical potential wells with high photon number. In this case, so what we would expect in the transition is within the transition is to have a highly mixed state within the transition. So we will expect the transition to be the state to be a statistical mixture of the both kind of solutions within the transition. And we have kind of see a small peak around the transition region. The problem is that when we look at the expected spectral gap within this method, or what we obtain for the spectral gap, is that we don't see any decrease of it in the transition region. So this, which is what we would have expected for a finite size system. We would have expected that within the transition region, the gap should decrease and there should be a slowing down of the dynamics. So from this, we take that we're seeing a regime of that's very far, still too far from the semiclassical limit, for the two semiclassical limits to see, in order to see the effects of the finite size effect. Another thing we can check another thing we can do to check the accuracy of the semiclassical approximation is to look at how Gaussian the steady state is. So as I commented before, in this approximation, in the semiclassical approximation, all the states are Gaussian, all the states is Gaussian at all times, and we can look at how Gaussian it is to check the accuracy of this approximation, and we do this by looking at the difference of Berle entropies between the true steady state and the a Gaussian state which has the same first and second moments as the first one, as the true steady state. And here this Q is just the Husimi distribution function. And what we obtain in this way is that this measure should give 0 in the case of the state being truly Gaussian, truly Gaussian state, and we obtain here then that the state is only Gaussian before the transition, but during and after the transition the state is not Gaussian anymore. For reference, for example, here we see that this measure gives 0.1 for a number 1 Fock state. Okay, this means that after the transition, the state is still far from being a Gaussian state. Now I'm going to start with the second part of the talk, which is a different kind of semiclassical approximations for this system in order to get more closer to the semiclassical limit. If someone has a question or maybe a comment now, I can hear it, and if not, I can keep going with the. Again.
I think we're okay here. I don't know if anyone online has a question.
Okay.
No, I think we're good.
Okay. So what we're going to do now, I'm going to comment a little bit about of the semiclassical approximation. So the semiclassical approximation that we were using before, it consists of taking the classical equilibrium values and then considering that the state of a system is given by a Gaussian state, each centered around these classical equilibrium values. So what we try to do now is use a different semiclassical approximation, which doesn't require the states to be Gaussian and and also takes into account superpositions of both kinds of solutions, as we have seen in the previous Husimi distribution functions. So in order to do this, we take the Limblad equation for this system and write it as an equation for the Wigner distribution. The Wigner distribution is another phase space distribution. And what we do now is use very widely known and a widely known semiclassical approximation, which consists of taking the all the derivatives on this equation that are of order 2, of order higher than 2, and just truncate all the derivatives of order higher than 2. And then what we get is a Fokker-Planck equation for the Wigner distribution. And in this case, the unitary part of the dynamics is mapped onto a Poisson bracket, and the dissipative part of the dynamics, it gets mapped onto this term here, which contributes both to the drift and the diffusion coefficients of the Fokker-Planck of this Fokker-Planck equation. For example, here we have some results within this approximation, and we see that it's pretty easy to get now superpositions of both kind of solution of classical solutions. Here we have a comparison of the different approximations. So for example, here in light blue, we have the classical equilibrium, the classical equilibrium values, and in this dot blue line, we have the semiclassical Gaussian approximation. We can see here, for example, that in the regime of large pumping, we have an instability, and this is because we are in this model, we are not including a mechanism of dissipation directly over the ion motion, and it's the only dissipation mechanism for the ion motion is indirectly through the cavity losses. And we can see here that in the black solid line, this is not a problem in the exact solution. And with this approximation, with the new approximation that we're trying, that's again a very widely known and widely used approximation, we see that this gets clearly more accurate results as compared to the exact results. So now, with this new approximation, what we can do is to take some assumptions about the semiclassical Gaussian approximation. For example, within this approximation, as I commented briefly before, the transition point of what is considered to be the point of the transition is usually the change of global minima in this effective potential across the transition. So, for example, if we take typical experimental values for these systems, then the distance between the optical potential wells corresponds to something between 2.5 or 7 for these ytterbium ions. And what we see is that in order for if we take the system to a regime with a very sharp transition, in order to more or less see where the transition is happening, then we need to get this distance between the optical potential wells to very unrealistic experimental values in order to see that the transition approaches this change of global minima, which is indicated here by this vertical dashed line. And this is in the row below, and in the row above. And in the row below, what we can see is that this is independent of the number of photons within the cavity. Even if we increase independently the number of photons within the cavity, then this is still the case. Then we're still far from the semiclassical limit for these typical experimental values of the system. Again, what we can do now is to look at the decay towards the steady state. For doing so, what we do is take that we have a two-state model, a kind of two-state model, which one of these states is the ion localized at the trap center, and with low photon number, and the ion localized at the optical potential wells with high photon number in the cavity. And with this in mind, we can look at the mean first passage time between both kind of regions in phase space, and we can derive then the decay towards, or we can check the decay, how's the decay towards a steady state. And here now we obtain that there is a slowing down of the transition of the decay towards the steady state as we approach the semiclassical limit. Here, each of these curves corresponds to a different value of the distance between optical potential wells. And here, for example, the figure at the left corresponds to a fixed cavity loss rate, and the figure on the right corresponds to a fixed mean photon number within the cavity. And here we see that there's a slowing down of the decay within the transition region, and this is not shown or maybe this is not clear from the figures, but this region is very small compared to the semiclassical bistable region. So again, this shows that the transition is located at a very different point from the semiclassical Gaussian approximation. In order to verify the results from the previous slide, the ones from the decay towards the steady state, we checked the validity of the results with a comparison on a small number of points using the quantum trajectories formalism. In this, the equation for the evolution of the open system is described by an ensemble of individual trajectories of this effective Hamiltonian. And what we see in this case is that, first of all, we see a good agreement between the quantum trajectories and the exact solution, the ones from the results obtained from the diagonalization of the Liouvillean. And what we see here is that there is a qualitative agreement between the truncated Wigner approximation and this formalism, the one of the quantum trajectories, meaning that we see a slowing down of the decay towards the steady state within the transition region, and we see the right order of magnitude, but there is a clear difference, nevertheless, between the results. So the decay rates towards the steady state are a little bit faster on within the quantum jumps approach. But nevertheless, they are of the same order of magnitude. And well, as a summary, we studied this system, the few-photon limit. We made a comparison between semiclassical and exact results. We saw that the semiclassical Gaussian description does not adequately describe the system within this regime that was the few-photon limit. We didn't see any decrease on the spectral gap, even though we saw an increase on entropy of the phenomenon entropy. And from this, we took that we needed to see larger systems in order to see the finite size effects of the classical bistability. For doing so, we use a different semiclassical approximation. We use the truncated Wigner approximation. We saw that even in this case, where we can see now the effects of the slowing down of the decay towards the steady state, still the Gaussian approximation performs poorly in this regime, and there is well, we saw that also the global minima of the effective potential does not describe adequately the transition point or the transition point. And we saw this minima of the decay rates within the classically stable region. Some future steps for this problem could be studying more classical systems, again using this approximation. For example, increasing the system size with more ions and considering situations similar to that of the Frenkel-Córdoba model, as I was saying before, or the sliding pin transition, or maybe the linear to zigzag transition. And what we're doing right now is doing, in the case of the Frenkel-Córdoba model for small systems, we're doing a characterization of steady-state entanglement using the semiclassical approximation, but far from the regime of bistability, far from this transition region between the two kinds of states. That's all.
Does anyone have any questions, or maybe sort of anybody online? You're welcome to ask as well.
I'm an experimentalist, so I've listened more on that perspective, and I would just like to know, you have shown pictures in the beginning, but how many of this bistability has been measured now in an experiment, or is it something that's at the moment only theoretical investigation?
If it's something to measure, so what particularly, I think for sure there are people working with these systems of ion traps integrated to optical cavities. So I'm sorry, the question was if there is something that could be measured in a
whether this bistability is something that has been observed experimentally.
Okay, so I think the problem here is that experimentally, I think experimentally you would have an you would see a kind of hysteretic behavior. So I think I'm not that sure, but I think in an actual experiment you can see. So for example, if you, I don't know, adiabatically or slowly increase the laser pump, then you should see that you stay on on one of the semiclassical branches until this branch gets completely unstable, and then you jump to the other one, and you should see the same thing from the other side. I'm not sure if it's how you could study a decay towards this steady state. I'm not that sure. I'm sorry.
Thank you.
Thanks. Any other questions? Well, if not, I also had a question. Yeah, I'm not an expert on this, so it's just a general question. Why? So combining the optical traps with the ion traps is what, like, does that give you, like, sort of what, like, extra thing does that bring? I mean, does that give you some, like, additional control over the ions, or is it like, are you interested in measuring some specific properties, or why would you want to combine these two things?
So it has some uses. For example, this study of the for example, I'm sure that you can do lots of stuff. For example, one recent thing you can do with this is use them as source of indistinguishable photons. Or another thing you can do that you couldn't do in it's just ion traps by themselves is study the dynamics between of this Frenkel-Córdoba model, the model for microfriction, because in order to study this model, I'm sorry, I'm going to go back a little bit. In order to study this model, so this model of friction consists of this chain of oscillators moving on top of the periodic potential, and the periodic potential is given by the field inside the cavity. So, for example, if you don't have the cavity, then the ions are the position between the ions, the dynamics is given by an harmonic trap. That's all.
Yes.
Okay. So for example, you can use these systems to study to stimulate dynamics of the Frenkel-Córdoba model, for example. Okay,
that's very cool. Thank you. Thank you.
Also, and that's very important use of this. You can also use this the action of the cavity. So the presence of the cavity can be used to cool the ion motion. It's very important in these systems to keep them close to or to take the most of excitations that you can out of the system in the ion chains. You need to cool them down. So this can be done with the presence of the cavity also. So you can use the coupling between the cavity and ion chain and the ion chain vibrational modes to cool them down. That's very important use. I'm sorry.
Yeah, no, thank you. Thanks. That's a nice explanation. I think there was a follow-up question. Oh, yeah.
Question. One of you, and sorry, I joined a little bit late, but on one of your slides, you mentioned the quantum trajectory method, and you had there a reference from 2014. Is that a special method, or is it just?
No. No, I'm sorry. I just picked a random reference. I'm sorry. I know it's.
No. I'm wondering whether some special.
No. It's not completely random. It's a good review on the quantum trajectory, but it's of course, it's not the first one. Nothing like that.
It's a review for many body systems. So it's application of optical objectives.
Thank you.
I still have a question which I missed. So you were describing there was a delta that describes the tuning of the light in the cavity from I would assume the nearest transition of the atom. I was wondering, how far are you from that transition? Is the atom at any time in this process making a change to a different electronic transition? Or must I interpret it as you are far away from any electronic transitions?
I'm sorry, could you repeat the question?
Or is your optical trap frequency, is it very far from any resonances of the atom, any transition that the atom could make to an excited state, or is it close to a resonance?
No. The idea is that the optical frequency, the frequency of the trap you said, or the frequency of the cavity?
Trap light, of the light in the trap.
No, of the light in the trap. Ah, okay. No. It's very far from the system.
Very far away. Okay. Thanks.
No, the idea is that the idea is that it's very far from the transition. So it is in such a way that you can consider this as a two-level system.
Yeah.
Okay. And also it's very important in this case to not get excitation to the steady state, to the excited state.
Okay, yeah.
Perhaps the last week. Hi, Alan. You, I think, use negativity as a measure of entanglement, correct?
Yes.
Can you just quickly explain this part again? Because I see the increasing negativity in your slides.
But I didn't show the negativity, but yes, we use the negativity.
You mentioned the summary. Just mentioned the summary.
Okay. So the idea here is that for Gaussian states, the negativity or the logarithmic negativity, actually the logarithmic negativity is a good measure of entanglement for these systems. So yes, we just check that within the classically bistable region, there is an increase in the entanglement as measured by the logarithmic negativity. The problem is that, and this is not a Gaussian state, so it's not truly correct to use this to quantify to think that the logarithmic negativity just quantifies entanglement. I think it's just a witness of entanglement. That's all. But we did see an increase, but it's not really a measure of entanglement. So yeah, there is entanglement in the system, but the increase, I don't know if it's so meaningful, the increase of the entanglement of this measure of entanglement within the system. Nevertheless, we also looked at for example, the mutual information, and it shows the same increase. So for sure, there are correlations in the system that are increasing during the transition. During the transition.
Carol?
This is a sort of more broad question, but like, are there any exciting applications of this for like new technologies or anything that are obvious at the moment that you can think of?
Applications for new technologies. No, I cannot think of anything. I mean, maybe I'm sure having a source of indistinguishable photons is useful for it has to have lots of applications. I know lots of people are trying to get photon sources or individual photon sources. I don't know any actual applications or technological applications of these systems besides that.
I would be surprised if it is applied whether use these chains for qubits, because you option to space them, and so I won't be surprised if it's used, but they won't tell us because that's obviously the secret.
Yeah, like proprietary. I just want to double check there's no questions online. I don't see. How do I see that? Would it pop up?
It's set up as a meeting, so they should be able to just unmute themselves and.
Okay.
Will you click on the list of participants to see who they ask?
Yeah.
Yeah,
Ilya, I don't know if there's anyone online who has a question.
Not as much as I could see.
Okay. Okay. Thank you. Okay, then I think if no one has any more questions, maybe we can just thank the speaker again.
Okay. No, thank you. Thank you.